All right, right. Okay, good. Today what I'm going to talk about is a very famous kind of technique called the Four Russians technique. And this is a general method that allows a surprising speed up in a number of different applications. We've been very heavily utilizing this in some of our research here on RNA folding. But the application I'm going to tell you about is the original application that was developed by Four Russians. The name of the technique Four Russians is due to the four authors who came from Moscow at the time, or lived in Moscow at the time. I've since been told by one of the authors that actually either three of them or none of them are not Russian ethnically. But at any rate, this has been known as the Four Russians technique, and it's for bit matrix multiplication. So in bit matrix multiplication, the problem is that you have two bit matrices. Just make up a 4x4 example. Something like that. And that's for A. And B, something like that. And the result is, in terms of the original definition, is just like matrix multiplication, except that instead of doing adding, you do multiplication of element by element, but then you don't add, you take the OR. Okay? So, for example, if we take the first row here, by the first column, that won't give us anything different than normal matrix multiplication, but let's just do it anyway. 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, and 1 times 0 is 0. So adding those up or taking the OR of all those zeros gives you a 0 anyway. Now, hopefully we have one where we get something different. Yeah, here. Let's take the third row and the second column. Now, if we did a normal matrix multiplication, this would be 1 times 1, which is a 1, 0, 0, 0, 0, and 1 times 1, and you'd add those up and get 2. But instead, we're going to be ORing, so it's 1, ORed with 0, which is, of course, 1, ORed with another 0, which is 1, ORed with 1, so a 1 OR with 1 is just a 1, not a 2. So the third and second position here is a 1. So again, the individual operations are just normal multiplication, or because these are binary, you can think of them as an AND if you wish. But multiplication of individual bits, but then the elements that we sum up, it's really an ORing of those individual bits and not a normal arithmetic sum. Does that make sense, what that definition is? Okay, good. All right, so if we just follow the normal definition, if this is an n by n, let's say we have two n by n matrices, following the normal definition that I just laid out here of bit matrix multiplication, each row by a column would involve n scalar multiplications, or ANDs if you want to think of them that way, and then n minus 1 OR operations. And so since we have n squared individual entries here, and each one of these row by column operations takes order n time, this normal definition of bit matrix multiplication would take theta of n cubed bit operations. And what I'm going to show you today is that this can be improved. And again, this cubic time seems sort of given by nature. It's hard. It was hard for people initially to think that that could be beaten because it comes out immediately from the definition, and it seemed to be difficult to divorce the definition from how else you might actually do this computation. Let's call this C. Okay, but the result we're going to get to is running time n cubed divided by log n. Okay, I don't specify the base of the log because bases, logs of different bases only differ by constants, which will then get swallowed up by the big O notation. So let's say this is log base 2 for example. If n was 10, right? 10 cubed is 1,000, right? Oh, but this is only log n. So that isn't it wouldn't be a huge improvement. Maybe you would division by 3. Log base 2 of 10 is a little bit bigger than 3. But let's say n is 1,000. Okay, so log base 2 of 1,000 is 10. So this would give you a speed up of a reduction in running time down to 1/10. Although there's sometimes some larger overhead involved in the method. But in our experiments with fluorescence in RNA folding, we're definitely getting noticeable speed up, factor of 5 or 10 over realistic ranges. So what looked initially like a purely theoretical result, although a very significant and important one, actually does lead to some practical methods as well. Okay, so to get into the Fluorescence method in this particular application, it's useful to change the perspective, how we think about bit matrix multiplication. Instead of row by column operations, we can cast this as just row operations. So really what's happening is that each row, let's take row 3 because we knew it did something interesting. Each row here is really specifying by the ones that are in the row, it's specifying a subset of rows in B that should be ORed together. So this row 3 specifies row 1 of B and row 4 of B. So if you look at those two rows, row 1 and row 4 of B, and if you OR those together, you get 0, 1, 1, 1. And the claim is that is what is row 3 of C, 0, 1, 1, 1. So row 3 here of A ends up specifying, along with B, of course, what row 3 in C is. And it does it again by specifying which rows in B should be ORed together. Well, this just takes a little playing with, or doing a little bit of transformation in your head, because the normal definition has row 3 here multiplying by column 1, but the effect of it is that picks up here, it's an ORing of those rows where there's a 1 here in row 3 of A and a 1 in well, another 1 in row 3 of A. So if you do that kind of mental transformation, which I personally find difficult, but I have to play with an example each time, and then it finally gels, we can think of a bit matrix multiplication in the following way. So this is an alternative way to think of bit matrix multiplication is that row I of C, the end result, is the OR of a subset of rows of B, and specifically a subset, let's call it S, of rows of B, and specifically S is the set of positions in row I of A which have entries of 1. Okay. So this is just writing down what I was saying earlier by example. So we can look, let's say, at what's row 1 of C going to be. Well, according to that, we have 1s at position 2 and position 4 of row 1 of A, and so we should order together row 2 and row 4 of B, and so that's 0 and 0, 0 and 1, 0, 1, 0, 1. So we should get 0, 1, 0, 1. Did I do that right? 0, 1. So multiplying, if we just do the standard definition, this would be a 0 in the first entry, and then but a 1 in the second entry, and then 0 in the third entry, and then a 1. Here's another 1, but those OR together to be a 1. So we get that. And that's the same thing as ORing together row 2 with row 4. Okay? So that's the important thing that happens here. So, given this fact, what's really happening is each row here is the OR of some subset of rows in B. So, making sort of incremental progress here, not saying much that's different here. Each row of C is the OR of some subsets of rows in B. And some of those subsets are the same. They would be the same if we had 2 identical rows in A. And some of those subsets, one is a subset of another row. I don't have an example. Well, yes, I do. The subset specified by row 4 of A is a subset of the subset specified by row 3 of A, because row 3 has a 1 everywhere row 4 does. Okay. So you can kind of think of that maybe we could speed things up a little bit if we could take advantage of the fact that some of these subsets are related to other subsets, and so on. All right, so one extreme version of that, can we use this idea to speed up the algorithm? Well, actually, in a practical sense, we can in a simple way, because if we just look at a particular row in A, that row, this row, for example, is specifying 2 rows in B, and it says we just have to do an ORing of 2 rows, and each row has n elements in it, and so that because it's 2, we end up with just n single OR operations. And that gives us row 3, that gives us row 2. And that certainly was a savings compared to multiplying every entry in row 2 times all of the columns in here. Basically, that's saying, well, the zeros are irrelevant here, so we could just ignore the zeros anyway. Okay, but that's only a practical speed up. That's not a worst case speed up. So what else can we do? Well, again, we're focusing on the idea that these are subsets. Each row of C needs some information from some subset of rows in B. So one idea is sort of a pre-processing of B. We won't even look at A yet in this pre-processing. We're just going to focus on B. And I'm going to need some more board space, so let me go over here. So pre-processing of B. One thing we could do is form every subset of rows of B, and for each subset, I'll call it S, form the, or compute the OR of the rows in S, and put the result in a table. So before we do the time analysis, let's just think a little bit more about the implementation of how you would, how you might want to do this. We'll ignore the issue of how you're going to generate all the subsets, although that's certainly simple if you just generate all the binary numbers. So just a little bit of implementation. We can think of all the binary numbers. That example was 4 by 4, so you think of all the binary numbers on 4 digits, etc., all down to 3, 4. So you could have all of the binary, so 2 to the n, binary strings of length n, and for each one of these, each one specifies a subset of rows from B. So this one is row 3, row 4, and you do that calculation, the ORing of 3 and 4, for example, 1, 1, 1, 1. Put that in the table, 1, 1, 1, 1. Put it in the table, and now you've generated all of the ORings that would happen from all of the subsets of rows from B. You never even looked at A yet. Okay, this is all just pre-processing of B. And then what would you do when you actually want to do the multiplication? Well, you'd look at a row of A. Now you actually have A, and you'd look at a row, and you'd see a particular string of bits of length n, and then you could just go to the table, look up that particular string of bits, and read off what that particular string of bits, this little example was 0, 1, 0, 1, somewhere in the middle here, 0, 1, 0, 1, and then you just read off what the pre-processed answer was, and you get that for C. Okay, now, this exercise of pre-processing of B was just to get your intuition going a little bit. This is not the full 4 Russians idea. Okay, because the pre-processing involves the generation of 2 to the n, not only 2 to the n binary strings, so that takes us 2 to the n time, but 2 to the n, then we have to do 2 to the n different unionings. Each union, well, most of them are not going to involve n different rows, but we don't, maybe we could do a little bit of analysis and some arithmetic and get it more exact, but in a kind of a rough analysis, we'll say each one of these subsets might require ORing together something on the order of n rows. And each row has n elements in it, so each OR takes something on the order of n squared operations. So each OR takes, well, in terms of an upper bound, we're going to say takes order n squared bit operations. So the preprocessing alone preprocessing takes order 2 to the n squared operations. And that's even before we look at A and therefore start creating C. So we went from an algorithm that had running time n cubed, but we weren't happy with n cubed. Yeah, n cubed, okay. And then through 20 minutes of thought, we've come up with an algorithm that's 2 to the n squared, okay? Now even, well, this is definitely vastly bigger than n cubed, unless, of course, you make the mistake of saying, well, since this only involves 2's and n's, and the other one involved n's and 3's, and maybe you think n cubed is bigger than 2 to the n over n squared, but if so, don't take bets involving powers of n. Anyway, 2 to the n squared is vastly larger, grows vastly faster than n cubed. So we certainly haven't made much progress here. But, believe it or not, I have actually introduced something of the spirit of the four Russians idea. And so, and I wanted to do it this way to get your mind going in this direction before I show you the details, because sometimes it's hard to see the idea in all of the details. So the four Russians idea will still pre-process B even before you see A, and it will calculate ORing of certain subsets, many subsets. So it's not going to pre-process all of the subsets. It's not going to generate all of the subsets of rows of B, but it's going to generate many subsets of rows of B, even before we see A. We don't even know which subsets are relevant, but we're going to do it anyway. So let me say now we are talking about the four Russians, and okay. And hopefully I can use this part. And so here's what the preprocessing, the four Russians preprocessing of B does. It first of all divide B, the rows of B, into groups of non-overlapping, disjoint groups. To disjoint groups of T rows each. Now T is just a parameter that we'll later specify, and it could happen, of course, that the number of rows of B is not divisible by T, but then we'll just have some group that's slightly smaller, that's smaller than T. It'll be that last group that doesn't quite have T rows in it. But these are minor details that we can clean up later. Or you would clean up if you're actually writing a program, but to get the general idea, we don't have to worry about that little issue. So you can imagine, if you want, that B, the number of rows of B is a multiple of T, even though we don't know what T is. And then, in each group, call it S, of T rows, we're going to find the OR of the rows in S and put the result in a table. Okay? So this table is going to be, again, how do we build the table? Well, each subset of rows, in each row, T rows, find the OR of the rows in S. Now, divide the rows into disjoint. No. I missed something in here. In each group S of T, in each group of rows of T, the important thing is we're going to generate all the 2 to the T subsets of rows of group T, of the group. Okay, we're going to generate all the 2 to the T subsets of rows of the group, similar to what we had earlier, where we're going to generate all subsets of B, but now we're just generating all the subsets of rows in a particular group, but we're going to do this for each of the groups. And then for each subset, for each such subset, we're going to form the OR of the rows in the subset and put the result in a table. Okay? So, yeah, this is the correct version. The last time I wrote this out, previously I missed the crucial step of generating all the subsets. So in a group of T rows, we're again going to generate all the subsets and form the OR of the rows in that subset and put those results in the table. So the first idea of forming all the 2 to the n subsets and taking the OR of all those 2 to the n subsets, that was essentially saying, let's let T equal n. But now we're going to parameterize on T and see that if we pick the appropriate T, this idea that at first looked really ridiculous, because it would give a method that was exponential time as opposed to polynomial cubic time, we'll see later at the end when we do the analysis that if we pick T appropriately, then this will actually give us the nice result that we want, that we're only doing n cubed over log n operations, including, of course, the time for the preprocessing, as well as the time for using the preprocessing to get C. Okay, so I think it's useful at this point to draw a picture. Draw a picture of what B looks like divided up into those groups. So here is B, and we're going to divide up into groups of T rows. So this is group 1 of T rows. And then we're going to have group 2 of T rows, etc., and go all the way down a little ways. So several groups in this little picture. 4. Oh, this one's a pretty big one. Let's make this so now we have 5 groups of T rows. And here's n. So in general, we have n over T. We can round this down, but anyway, n over T groups. Or is it n over T rounded up groups? Well, let's not be too careful, then just say n over T groups, okay? About. Okay, and inside each one in the preprocessing, we're going to form all of the 2 to the T subsets and then put those in the table. So what does the table look like? Well, inside each group, we're still specifying, each row is you can think of it basically as a binary number again, and but that's true, but irrelevant. Each group is still a subset of rows Okay? And therefore, you can think of that particular group as a binary number. It's not necessarily a binary number that's in B. But just as before, every group, every subset of a group can be specified by a binary number. In this case, now, it's a binary number of length t. So every subset of t rows is specified by a binary number of length. Now it's t. Okay, so it's a t-length binary number. Which particular rows in this subset are we going to have? And then when we do the ORing for a particular binary number, when we do an ORing of those t rows, we get a result. And so I can put it in a table. Let me look at the notes here, how I want to draw this table. Contents of unions. Yeah, okay, so for each group, so we could have a table for group 1 and a table for group 2, and so on. And in each table, we would have a t-bit binary number. So let's say 000, 001, 010, 100, 011, and so on. So this is a t-bit number. And then for each one, this is the OR. Well, make it a more interesting one. This is the OR of the specified rows of B. Okay? And then, so that's for group 1, and then we have for group 2, etc. Okay? Does that make sense? I think I'm being more detailed than necessary, and maybe that causes, that's more confusing to be so detailed. But at any rate, the tables we would now generate, we'd have a table for each one of the groups, and then in each of the tables, we would have the 2 to the t-bit numbers, and each one would specify a subset of rows of B that had to be ORed together, and those would be ORed together, and then we'd put that on the table. Okay, before we talk about what t is and how much time this takes, now let's think about how you use this. So you've done this preprocessing. If you let t equal n, this is utterly ridiculous. But if we let t be something smaller, then we'll see in a while that this is going to be a winning strategy. But nonetheless, think of just, we've divided B into these groups of t. We've done this preprocessing. We put the results of the preprocessing in a table. And now we want to actually do a multiplication. So let me write the multiplication, or draw the multiplication out in a little more abstract form. So here we have A times B equals C. Okay? And now I'm going to divide up A, this is A, B, C. Now, B was divided already into groups of T rows, okay, T rows each. Now we're going to think of A as being divided into groups of T columns. Okay, well, let's imagine that, okay. So in fact, if these are square matrices, we should have the same number of groups, 1, 2, 3, 4, 5, 1, 2, 3, 4, make this a little bit prettier. Five. Okay? So these are both square matrices, although we could actually adapt this to non-square matrices. But so if we divided the rows of B into n over t groups, then we're going to divide the columns of A into n over t groups. Okay. All right. Now let's think about doing the matrix multiplication. We've done the preprocessing, and now we want to do the actual matrix multiplication. Okay? Now the point is, let's just think of the first row here. Okay? This row specifies a subset of rows in B that should be ORed together. So let me make up some numbers here: 1, 1, 0, 0, 0, 1, 0, 1, so on. 1, 0, 0, 1, 0, 0, 0, 1. Not sure if that's going to be readable on the TV, but it doesn't really matter. The point is that this, if we think of the row as undivided initially, then where the ones are, that specifies a subset of rows of B that should be ORed together. Okay? To get the first row of C. That's what we've been saying is what matrix multiplication is really about. Each row of A specifies a subset of rows of B that should be ORed together. But now with the preprocessing, notice here's the punchline. Here's how you take advantage of the preprocessing. In each group of columns in T, each group of columns in A, each group of T columns in A, that specifies a binary number which specifies a subset of rows in B. What group, so this is row 1, well, this is group 1, the first group of this row, and the binary number that's shown there of length T specifies some subset of rows in B. Which ones? Can you see which ones?
Just the first subset and whatever 0, 1, 0 maps to in group 1s.
Yes. Yeah, the point is that because this binary number is in group 1, it's in group 1 of the columns of A, the binary number that's there specifies a subset of rows in group 1 of the rows of B. And similarly, the binary number that's in group 2 of the columns of A specifies a subset of rows of group 2 of B, and so on. So every binary number in this particular row, and I'm illustrating this with row 1, but it could have been any row, every binary number in this row specifies a subset of, of rows in a particular group in B, and if you're in group I of A, it's specifying a subset of rows in group I of B. And this binary number that we're seeing here can be used as an index into the appropriate table. If we're looking at group I of columns of A, then the binary number that we see there in that particular row is going to specify a subset of rows in group I of B that should be ORed together. But we've already ORed them together in the preprocessing, so we just look it up in the table and then we have it. So that would give you then the OR for that group of B. So what would we do to actually get the full elements in, let's say, row 1 of C? We use this binary number, and look up from group 1 what the result is. It's an n-length vector from group 1 in the table. And then we look up with this binary number with the result from group 2. And what should we do with those two results? So this gives you an n-length binary number, this gives you an n-length binary number. What should we do with those two? Yeah, we want to OR those two together. And then we look up, use this as a lookup, and we OR those together with the ORed result we had, and so on. And in the end, that gives us what should be in row, in this case 1, but in general in row I. So that's the method for how you use the preprocessing. Let me try to write that down a little bit. This was the preprocessing. I want to write down a little bit how we use it, and then we're going to do the analysis, because up to now, well, the only analysis we did was if we were going to generate all the 2 to the n subsets, and that was certainly silly. Now, we'll do an analysis in a minute that shows that this is not so silly. But, so using the preprocessing to, let's just say, get row I of C. And so what you do is, for G equal 1 to n over t. And again, I'm going to assume that n is a multiple of t, so we don't have to worry about groups that are not full. But for G equal 1 to n over t, we look at group I of A. Okay, so you look into the ith group of t columns of A, and using those entries, those t entries, as a t-bit index or number. Think of that as a t-bit number. As a t-bit number and an index to table I, the preprocessed ith table. So you're going to use that, the t-bit number that you find in the ith group in A as an index into the ith table that we preprocessed, the ith table I for B. And then we're going to OR those entries. Running out of space here. OR those entries with what? Let's say row I of C. Initially, it'll just be the whole zero length, 0-bit n-length vector. So we're going to start out in what we know about row I of C is just the all zeros. And then each time we get an n-length vector from one of these tables, we OR that with what we have. And in the end, once you've done this, then that's row I. Okay, so I don't have room here, but just at the end we output row I of C. Okay? So this is just writing down in some kind of awful pseudocode that's too cramped and messy. But anyway, what I was doing over there by example. Is that clear?
Yeah.
Okay, so it works. Certainly you can you can do your matrix multiplication this way, your bit matrix multiplication this way. There's certainly more overhead here than the normal definition, but it works. But why would you ever do it? What is the point of this? Okay, so let's go through the analysis, including of course, including the preprocessing time. Okay, so analysis. And we're going to still use T, okay? So we have N over T groups. N over T groups of B that we're going to look at. And in each one, we're going to generate 2 to the T subsets, okay? Well, we're using the binary numbers, 1 through 2 to the T, okay? So I guess I should put that in there as well. We want to generate analysis. Generate binary numbers there's 0 through 2 to the T. I guess it's 2 to the 3 minus 1. And these are going to be the specifiers of subsets. And then for each group, for each N over T groups of B, we'll generate the 2 to the T subsets of rows, or locate. Generate is probably the wrong word, just pull out. And then OR those or each subset. Okay, so when you OR each subset could be as big as T rows, and each row is length n. So that looks like Tn. This looks like T times n operations when we OR together a subset of T rows. Okay. We have 2 to the T subsets that we're going to do this for. So 2 to the T. Okay, 2 raised to the T. And then we're going to do that for N over T groups, right? So for each of the N over T groups, we look at all the 2 to the T subsets, and then we OR together the appropriate subset. And so we've got N over T here. Well, I hope this works out. So it looks like the preprocessing takes N over T times 2 to the T times T times N operations. Anybody have any objections to that? Maybe I should check my notes to see whether they agree with me. Well, they better. I can't find exactly where it's written, but let's just see what happens when we do this. So, okay, I haven't told you what T is. I've been holding that off for a while. But let's just, and you can do some kind of analysis that tells you what T is, and the notes kind of do that. But let me just, spoiler alert here, T, let's just take T to be log n. Okay? You can think of any base you like. Log base 2, let's say. Okay, well then what is this? This is n over log n, just plugging in for T, times 2 to the log base 2 of n, which is just n. Okay. T here is log n. Oops, this is not looking good.
Actually, I think that t times n, the t is unnecessary. I don't think you need the t. T times n, I think it's just n.
Okay, and why?
Because you times n over t entities together with each other.
Oh, yes, yes, yes. Okay, yeah, thank you very much. Yes, we can get rid of this t, and that's very important that we do that. Because let's just take this one step further. I was about to get n cubed here, and that wouldn't have been good. This t is not necessary, okay, because each subset, I was counting to order together the subset of t rows as t times n. But that's if we do everything from scratch. That's if every time you look at a particular subset, you say, I never did anything previously, I'm just going to OR those together. But in fact, you can, if you look at the binary numbers in terms of the number of ones they have in them, you can OR together, well, each subset only has one row in it. There's no really ORing in there. Then you OR together all the subsets of 2 rows, okay, and those are done. And then, if you want to OR together subsets of 3, well, a subset of 3 rows is just the ORing of 1 row with a subset of 2 rows. But you already have all the subsets of 2 rows. So that, getting the result of the ORing of 3 is just n additional individual OR operations. Okay, so this takes a little bit of organizing of how you're going to do the ORing, but it really is just a matter of well, it is a little bit of organizing, but I claim that can be done so that each new result that you're going to put in the table, each new row that you're putting in this table, only takes n additional bit ORs, not t times n bit ORs. Again, if you're going to look at a subset, let's say, of k rows, you OR one of those rows together with the result for having ORing of k minus 1 rows, which you already have available. Okay, so we can take out this t here, and then we're in better shape. Okay, so n over log n, 2 to the log n, which is just n. Now we're taking out this t, which was log n, times n, and now we have n cubed over log n. So the pre-processing, which was so hideous and ridiculous if you looked at all of the subsets of B and took all the 2 to the n subsets of B. Now when we do it this way, we're only taking subsets of t rows at a time, and we pick t to be log n. So for t equals log n, the preprocessing time is just n cubed over log n. Okay, that's preprocessing. Now, when you actually do when you actually use the preprocessing result to do the multiplication, what's that time bound? So okay, just looking at the pseudocode here, we're going to do something for every row, and there are n rows there. This is really going to make the board work awful. I'm going to do refer to the pseudocode here, but do the analysis on this board for multiplication, the actual multiplication itself. And so we have n rows, okay, and then we have, for each row, we have g goes from 1 to n over t, okay, so we've got n over t, let me write it out like this, n times n over t, okay, so t goes from 1 to n over t. And what do? We look at a binary number, a t-bit binary number from A, take that, if you want to call that, you want to look at individual bit operations and call that time t, you can do that too. Okay, I hope. We're a little worried about that. So you look up that, you grab that binary number, and you use that then to look up the result from B. Okay, and then we have to OR those together. So the ORing of those together is n over t ORs times, this is looking terrible. I should have practiced. Okay, so this one is supposed to be actually the easy one. So we have n rows, and G has to go from 1 through n over t. So in each one of those rows, then we're going to grab a binary number, which I'm going to pay for because I want to be totally explicit. So that's t bits. But you're using that as an index into the table. You're pulling out a, why did I?
That's just n. So for each row, it's n over t times n OR operations. We're looking up n over t rows,
yeah.
And order them all together. That's right. So it's n over t times n OR operations among all of them, I think.
Right. Okay, yeah. All right, so it's n individual rows here, and then n over t groups, and for each group, we're going to pull out a binary number of length t, and then we have to OR those together. And you're pulling out a binary number of length n, and you're ORing those together. So that's each one of those ORings is n, and this is n cubed over log n. And the only thing that slightly bothers me at the moment is that haven't quite included the time that's needed when you're pulling out that binary number from one of these groups in A. If you look at every one of the bits, then we should be.
I think it's it's n times parentheses n over t times n plus n over t.
Yeah. Okay. So this isn't complete yet because we haven't included the time to actually look at the bits and use them as indices, but that only adds, it doesn't multiply. So over an entire row, okay, this is a row in A where we divided the columns into size t. I want to say, yes, it's going to take time t to use this as an index, okay? And yes, it's going to take time t to use that one as an index. And so for each row, we have time t, and we have n over t of these, okay? And then we have n rows. So altogether, this contributes another n squared to the total algorithm. So using the bits, using the binary numbers as indices, contributes another n squared to the time. And so we have order n cubed over log n plus order n squared. But of course, this one already subsumes that, so that goes away. All right, well, almost an on-time arrival. So it got a little bit rough at the end here. I should practice more before I come in to do the lecture. But next time I do this, next year or whatever, maybe tomorrow, it should be a little smoother. And so that's it. So I hope everybody understands it and appreciates that we get this theoretical result, n cubed over log n, and it's actually practical. If you do a little bit more analysis of this, it turns out that there are other choices for t that are even a little bit better. That if you do the analysis very carefully, you can get a constant. You can see what the constants are in this analysis. And then there's a t that you can choose, which doesn't reduce the asymptotics, but does reduce the constant. And I may ask you to do that for homework. I don't quite remember what it is right now, but for homework I may ask you to look into the analysis for that one and see the improvement. All right, thank you.